Hello guys, good afternoon. Sorry we're running slightly behind this afternoon. Welcome to the GCSE Physics session. Today the focus is going to be on pressure in fluids, and it's going to be delivered by the amazing Preshayla. Preshayla, as many of you already know, is currently studying at Loughborough University, studying physics, and she's delivered many sessions with us here. For new joiners, just to let you know that this session will last an hour, so we'll be looking to end at 4:15, and as you can see, you've got some bits there that Preshayla will go over today. If you have any questions throughout the session, do feel free to pop them into the chat box or the Q&A function. Both are located at the bottom of your screen, so you should be able to access it from there. I'm going to hand over to Preshayla now, if you're ready.
Cool. Okay, so we'll just go through what we're going to cover today first. So not too much content today, kind of just little bits of information that I'm going to give you. I'm going to go through two equations, so not too many. We're going to go through what a fluid is, what the Earth's atmosphere is, and how does the density of the Earth's atmosphere change with altitude. Learn about what atmospheric pressure is, and how it changes with altitude, described why the pressure of a liquid is dependent on density and depth, and talk about the equations that govern that, and then be able to use those equations to calculate the pressure due to a column of liquid. Then we'll have hopefully 20 minutes for past paper questions, and then your questions at the end. Okay, so first of all, we're going to start with what actually a fluid is. So a fluid is, it can be a liquid or a gas. So you might think of fluids as only liquids, but actually it's liquids and gas. It just means anything that flows. So anything that is fluid is can be known as part of this group called fluids. Now, the pressure in fluids causes a force normal to a surface. Okay, so it causes a force normal to a surface. What we mean by normal is that same thing we did in refraction, which is that 90-degree line. Okay, so it acts at right angles to it. It's perpendicular to it. That's all normal means. Three kind of words for the same thing. So that's what a fluid is. And then we have this equation for pressure. So pressure is how force is spread over a certain area. Okay, so how widely spread is that force over a certain area decides what the pressure is. So it's force normal to a surface divided by the area of that surface. So pressure equals force divided by area as a simple equation, but it's important that it's actually the force normal to a surface and the area of that surface. So not just any random force, not just any random area, it's got to be really specific to that surface. So pressure determines the effect of a force, but what is pressure measured in? So pressure is measured in this thing called pascals. Okay, pascals is basically a special term, so a special kind of word that we give to newtons per meter squared. Okay, so force we know is measured in newtons. Area is measured in meters squared, it always is. So we know that pressure has the units of newtons per meter squared. But we don't call it newtons per meter squared, we call it pascals because of the person that invented it. Okay, so the unit of pressure is pascals. And we don't really tend to write out pascals, we just do its kind of abbreviation, which is a capital P and a little a. Make sure, again, I said this yesterday if you were there, that you get which one's the capital letter and which one's not the capital letter. It sounds really trivial, but it is really important. because if we have a small P and a big A, that means picoamps, which is something completely different and in the electricity topic. Okay, so it's really important that we do that. So how can I describe pressure kind of better to you using a real life example? Well, a good example that I like to use and that might help you to think about them in a more kind of realistic situation is shoes. So flat shoes spread force over a large area. Okay, so you've got the force of your weight, of your person's weight, going into the shoes, right? That's really where all their weight goes, is concentrated in their feet. Okay, so they need to have good shoes to be able to spread the force over a large area and reduce the pressure that the foot feels. Okay, it's not going to be very nice if you've got a lot of pressure on your foot, which is why in daily life we tend to wear good flat shoes with a large kind of sole. That's really good. However, high heels are obviously got a lesser surface area on the bottom, right? So you've just got the sole and then the heel tip. So high heels have all the force in a much smaller area than a flat shoe does, which increases the pressure, which might be why people feel pain when they wear high heels, because there's a lot more pressure acting on the foot. Okay, so it's the same force, same person, same weight, same force, but because it's a much smaller area, the pressure is increased. And if it's a much larger area, so a much larger sole, the pressure is reduced. Okay, so that's kind of a realistic way of thinking about it. Now, we've just said that if we increase the area, we reduce the pressure, which makes sense if we go back to our equation, because if we increase the area, so if we make the denominator much bigger, we make pressure much smaller. Okay, so sometimes I like to think about it using real numbers. So let's do 10 equals 20 divided by 2. Okay, so this means 10 is pressure, force is 20, 2 is our area. Now we make our area much bigger. So we have a bigger shoe, we have a bigger area for the force to act on. Same force, 20. Bigger area, let's go for 10. So our area has gone from 2 meters squared to 10 meters squared. And if that happens, we can see that our pressure also reduces by a lot. Okay. So our area times is by 5, but our pressure divides by 5 for the same force. Okay, so if area is bigger, pressure is smaller, and if area is smaller, pressure is higher. That's how it all fits together for the same force. So you might see it either as this equation here on the left or the simplified equation on the right, which is just P equals F over A. Okay, so that equation that I've just told you about is the pressure that we usually talk about when we're talking about solids. So in pistons, in kind of solid real life machine applications. However, pressure in a liquid is different. Okay, so if we have a container of liquid, a column of liquid, we have a very, very different equation. So let's take a measuring cylinder. You might have seen a measuring cylinder in school. So it's just like a column of a thin kind of tube of water, but it does work for any container of water. So this is the equation that we use. It's pressure of the liquid equals the height of the column times the density of the liquid times gravitational field strength. So it's really bringing in lots of different areas of physics into this one equation. Okay, so it's bringing in density of a liquid. Now, you may or may not have covered density before, don't worry if you haven't, but density is coming from a different area of physics. It's coming from that materials area where we do density equals mass divided by volume. Gravitational field strength, well, that's coming from earlier on in forces where we talked about gravity and gravitational field strength, and that's bringing that in. So really it's a lot of different concepts tied together in one equation. So it's really important that you understand each part. So what is density? What is gravitational field strength? So yes, we have our pressure equation for a liquid. What are the units then? So pressure, again, is measured in pascals. Height is measured in meters, like it always is. Density is measured in kilograms per meters cubed. Now, let's break away from that for a second and talk about density. So density is denoted by this Greek letter called rho. It looks really similar to a P, which is really annoying because we already have a P for pressure, but that's what it is. And so P is our Greek letter rho. Now that stands for density. We know that density is mass over volume. Okay, so that's our equation for density. Okay, mass over volume. Now we know that mass is measured in kilograms and volume is measured in meters cubed. So we can see that our units for density are kilograms per meter cubed. Okay, so we need to know that because we might have to write it in an exam question answer that the unit is kilograms per meters cubed. Now, the same for gravitational field strength. So let's break away now and talk a little bit more about gravitational field strength. Okay, so gravitational field strength is what we use when we calculate weight. So you might remember the equation F equals mg. Okay, or W, so equals mg. Now, all that is force equals mass times gravitational field strength, or weight as a more specific force is mass times gravitational field strength. So this is a way of working out force, right? Force equals mass times gravity. And it's how we convert our mass into a weight. Okay, and they're two very, very different things. Weight is a force, mass is just a value of kilograms. So when you step onto the scales are measuring your weight, and you weigh yourself and you have a weight. But the scales actually read a mass. Okay, so the scales are actually doing the work and they're converting a weight reading into mass by doing this equation here. That's what your scales do. They measure your weight and they convert it into a mass, which makes more sense to us. So nobody weighs themselves in newtons, right? But we incorrectly say that we have a weight. So two very different things, and it's important that we differentiate between the two. So looking to the units of gravitational field strength then, we know that gravitational field strength is this G. So let's rearrange our equation for G. G equals F over M. Okay, G equals F over M. Now F is measured in newtons. M is measured in kilograms. So the gravitational field strength is measured in newtons per kilogram, as we can see here. Okay, so pressure varies with depth. If we have a deeper body of water, the pressure is going to be higher. Okay, so a cup of water, take a cup of water, the pressure at the top is much, much lower than the pressure at the bottom of the cup. The same in this bucket here. If I zoom in on this picture, at the top, there's not much pressure. At the bottom, there's a lot of pressure. You might be able to tell because the water coming out of the top hole seems to have less force when it's coming out than this one. So it kind of just drips down. But the other one is kind of a big, fast jet that sprays out of the bucket because it's got a lot of pressure. It wants to get out quick. Yeah? So the deeper the water, the higher the pressure, which makes sense because the height of the column or the depth of the water at a specific point, if we increase that, we increase pressure. Okay? We increase that, we increase pressure. Now, this is due to the weight of the water in the column above. So at the top of the bucket, there's no water on top of that point. Okay, so we're sitting at this point, there's no water on top of it, so there's no pressure. But at the bottom of the bucket, it's got all of that water sitting on top of it, and therefore a much, much higher pressure acting on that point. Okay, so it's got lots of water above it, and it's got more pressure acting on it. Okay, so upthrust is another kind of key term that we need to know about. So upthrust is when an object that is partly or completely submerged, so underwater, experiences a greater pressure on its bottom surface than its top surface. Okay, so let's say we drop a little cube into the water. The bottom of the cube has a greater pressure than the top of the cube. So there's a greater pressure on the bottom of the cube than the top of the cube. Doesn't matter what the object is. And it doesn't matter whether it's completely under the water or just partially in the water. So because there's more pressure on the bottom than there is on the top, this causes a force upwards. This causes a resultant force upwards. This is known as upthrust. That force is known as upthrust. It's something that pushes an object up out of water. If the upthrust is less than the weight of the object sinks. If the upthrust is larger than the weight of the object floats. So if we have a bigger upwards force than we do a downwards force, the object floats. Okay, so if it's a bigger force upwards than downwards, the object's going to float. That makes sense. It's being pushed up to the surface because there's a bigger force going upwards. And then if we have if the upthrust is less than the weight of the object, then it's going to sink. So there's less force going upwards, more force going downwards. So the object will sink. Okay, so that's upthrust. Moving on to atmospheric pressure. So atmospheric pressure is talking about the pressure in the world around us, talking about pressure on Earth. Okay, so the atmosphere is a thin layer of air around the Earth. You might have heard of it before, you probably have. The atmosphere is just this thin layer of air that surrounds our Earth. It's quite thin in comparison to the Earth, so obviously our Earth is very big. The atmosphere is only a small fraction of the size of the Earth. Now, the atmosphere gets less dense with increasing altitude. Okay, so the atmosphere gets less dense with increasing altitude. What we mean by altitude is how high up we are. So altitude is how high up we are. And the air gets thinner, gets less dense as we go up. So the air at sea level is much more dense than the air in the sky that an aeroplane might fly at. Okay, and the reason that we have atmospheric pressure is because air molecules collide with a surface. So air molecules colliding with surfaces create atmospheric pressure. Constantly around us, air molecules are colliding, and therefore we have an atmospheric pressure. Now, the number of air molecules above a surface decreases as the height of the surface above ground level increases. So what that means is the higher up we are, the less air we have, the less number of air molecules we have. So as we get higher, as height increases, there is always going to be less air than at a lower height. So at sea level, enough air. As we get higher and higher, air decreases. The amount of air molecules in the air is just simply less. That is why atmospheric pressure decreases with height. Because there is less air molecules, there are less air molecules to collide, and therefore there is less atmospheric pressure created. Okay, so you need to know that kind of chain of explanation, which says that as we get higher and higher above sea level, the number of air molecules decrease. Because the number of air molecules decrease, we have less collisions between the air molecules. If we have less collisions between the air molecules, our atmospheric pressure will drop, because the thing that is creating the atmospheric pressure is this collision of molecules. Okay, so we need to know these two values here. At sea level, pressure is 101,000 pascals, sometimes written as 101 kilopascal. So remember, kilo just means 1,000 times by 1,000 pascals. So sometimes it might be written as that. And then cruising altitude, so the height that a plane normally flies at is known as cruising altitude. So as the plane is cruising through the sky, it's usually, on average, going to be at a pressure of 27,000 pascals. So you can see that the pressure is much, much, much lower than at sea level because it's much higher up. So pressure decreases as we get higher, otherwise known as 27 kilopascals. So you can do the same with that one there. So important to know how to differentiate between the two and know that that is just saying the same thing. So because we have such a low pressure in the air, planes must be pressurized. So we must have pressure in a plane, because if the air pressure is too low, we can't take in oxygen quickly enough. Okay, so if the air pressure is too low, humans cannot take in oxygen quickly enough, and that would cause asphyxiation, which is basically where no air can get to your lungs and can possibly be fatal. Okay, so planes have to have the correct pressure inside the cabin so that we can get enough oxygen, which is why in planes they are fitted with oxygen masks just in case the air pressure were to drop in the plane. Okay, so it's really important that we protect ourselves from this really low pressure. Another example of this is on really, really tall mountains. When you're at the top of a mountain, you can experience altitude sickness. Okay, so altitude sickness is where you can't get enough oxygen in your lungs to function properly. You probably won't die, but you might have a few kind of sickness, complications, that kind of thing. So yeah, it's definitely harder to breathe at the top of a mountain because the pressure is much lower. Okay, so that's all the content covered. So yeah, not much content today. We'll go through some quickfire questions and then try to get on to some past paper questions. So what is the meaning of pressure? Is it the force per total area, mass per unit area, or force per unit area? And then for the second one, what is the unit of pressure? Newtons, pascals, or kilogram meters per second? So put your answers in the chat or just think about it to yourselves. What would the answer to those two be? Okay, so the first one is force per unit area, and the second one is the unit of pressure, which is pascals. So force per unit area and pascals. So what that means is the force acting on a centimetre squared. A metre squared. Okay, so per unit area means the force acting on a metre squared of that surface. What is the average atmospheric pressure at sea level? So you need to think back to what we were just talking about. So this is sea level. Remember, I gave you two values. One was sea level, one was cruising altitude. So which one would this be? Sea level. And mathsy question here for you. We have a force of 10 newtons and an area of 2 meters squared. What is the pressure? So 2 minutes to think about the answer to those two questions. Okay, yeah, so the atmospheric pressure at sea level is 101,000 or 101 kilopascals. And then for the second one, a force of 10 newtons acts over a surface area of 2. So we use our equation P equals F over A. F is 10, A is 2. So we do 10 divided by 2 is 5 pascals. Well done if you got that. What are fluids? Are they liquids only, gases only, or liquids and gases? And what is the name of a force, of the force, caused by different pressures on the top and bottom of an object in a liquid? So remember, at the bottom of a liquid, there's a higher pressure than at the top of the object in the liquid. Okay, so fluids can be liquids or gases, and the name of the force that causes different pressures on the top and bottom of an object of a liquid is upthrust. What type of shoe is best for walking on snow? Wide shoes with a flat sole, narrow shoes with a jagged sole, or shoes with a sharp pointed heel? And which Greek letter is used to represent density? Mu, gamma, or rho? So which type of shoe and what Greek letter? Okay, so the type of shoe that is best for walking on snow is obviously not a sharp pointed heel. It's wide shoes with a flat sole. So if we have wide shoes, we have a big area. If we have a big area, we have a small pressure. If we have a small pressure, you're less likely to sink into the snow, right? If you have a high pressure, you're going to sink far into the snow. If you have a low pressure, that's better for snow. Why would we not have narrow shoes, I should say shoes, narrow shoes with a jagged sole? Well, narrow shoes would not be a very big area, and if we don't have a very big area, we have higher pressure. But a jagged sole is good, that can provide grip. And then shoes with a sharp pointed heel, well, that is not a lot of area and therefore an increased pressure. Which Greek letter is used to represent density? That's rho. So it's that one that kind of looks like a P, kind of annoying because pressure is also a capital P. But remember, pressure is a standard English uppercase P, and density is a Greek rho. So it's kind of more curved round like that. But yeah, look, very similar, so be careful. What happens to pressure in a liquid as its depth increases? So if we have a container of water, is the pressure going to be higher at the top or at the bottom? And in which direction does pressure act in a liquid? So as we get further and further in down a container, as depth increases, pressure increases. Okay, so the pressure down here is much higher than the pressure up here. And in which direction does pressure act in a liquid? It acts in all directions. Okay, so here we've got a really, really standard 3-mark question. So the question talks about a graph which shows how atmospheric pressure drops as altitude increases. So we can see that altitude increases on the x-axis and atmospheric pressure increases on the y-axis. So as atmospheric pressure drops, altitude increases. So why does that happen? Why does atmospheric pressure decrease with increasing altitude? This is a really, really standard 3-mark question, so it's important that you nail it and know exactly what to write and the key terminology that you need to use. Okay, so well done, I think Sheila. I don't know if that's correct, but the correct pronunciation. You've been getting all the answers right, so that's really good. And you got the right answer here. So the atmospheric pressure decreases with increasing altitude. So why does that happen? Well, at a higher altitude, at a higher height, we have less air molecules. If you have less air molecules, there's less collisions between air molecules. If there's less collisions between air molecules, there's not enough pressure created. Okay, so remember, it's that collision of air molecules that creates pressure. Okay, I'm going to skip that question. Okay, so here we have a diagram of hydraulic brakes. Don't worry too much about what hydraulic brakes are. It doesn't come up in your specification for AQA, but hydraulic brakes are basically, they use water to allow brakes to work more efficiently. So it's a better way of having brakes rather than just a clamp on the gears. So it works with the force from a rider's hand pushing down a master piston through the liquid. As it pushes the liquid through, that creates a pressure, and then it pushes another piston called the slave piston. So we have the master piston, then the slave piston. We've been given the areas of both, 5.6 times 10 to the minus 5 and 14.4 times 10 to the minus 5. So the difference in area with the same force creates a difference in pressure. This difference in pressure allows for the brakes to be applied. Okay, so the question asks, when the rider's hand pulls on the brake lever, the master piston applies a pressure of 1.5 times 10 to the 6 pascals to the liquid. So that's 1.5 times 10 to the power of 6 pascals. Now we know that the master piston has an area of 5.6 times 10 to the minus 5. So the area is 5.6 times 10 to the power of minus 5. So I want you to work out what the force exerted on the liquid is. Okay, so what is the force exerted on the liquid? So we need to use our equation, P equals F over A, and rearrange it for F. So rearranging for F means that we need to do P times A equals F. So to find our force, we need to do pressure times area. We've been given a pressure, we've been given an area, so what would the force be? I'll give you 1 minute to have a go. So remember, we're doing pressure times area to get the force. Okay, so we're just doing a simple multiplication of this value times this value, which gives you 84. So if you've got 84 newtons, well done. We'll do this question and then I'll take some questions from you guys. So the pressure in the liquid applies a force to move the slave piston. How does the force compare to the force applied by the master piston? So how does the force compare to the force applied by the master piston? So you might want to have a look back at the diagram. So we can see that the area of the slave piston is bigger than the area of the master piston, so 14.4 and 5.6. Now, because the area of the slave piston is greater than the area of the master piston, that means it's going to be a lesser, a bigger pressure. Okay. Okay, so question 3. Some students fill an empty plastic bottle with water. The weight of the water in the bottle is 24 newtons and the cross-sectional area of the bottom of the bottle is 0.008 meters squared. So we should be able to find the pressure using those two values, force and area. So what would the pressure be? So we're going to do 24 divided by 0.008, which is 3,000 pascals. So it says, and to give the unit. Now, pascals is the one that's commonly done. It's the one that we always use, pascals. However, we can switch it out for kilopascals. So if you wanted, you could do 3 kilopascals. Or you could even write it in newtons per meter squared. So if you can't remember pascals in the exam for whatever reason, you may be able to remember newtons per meter squared by doing force in newtons divided by area, which is meters squared. So you can even derive the units that way, and they will accept that. Okay, so newtons per meter squared or pascals. As long as you get a correct unit, they're happy. Okay, I'm going to take some questions now, just for the last 15 minutes. Okay, so does upthrust work with fish in the sea, or is it just objects? Upthrust does work with fish in the sea. So any object that's in the sea experiences upthrust. Any objects in any liquid experiences upthrust, because at the bottom of the object, the pressure is higher than at the top of the object, and therefore it's going to feel an upthrust. Somebody said, is there a symbol equation for pressure in fluids? So if I go back to pressure in fluids, yes, I probably should have drawn the symbol equation out, sorry for that, but it's just taking the symbol. So P is just a capital English letter P. The height of the column is going to be H. The density of the liquid is going to be our rho. And our gravitational field strength is just going to be G. So P equals H rho G. Okay, and then someone said, can you explain gravity? So gravity is just this force that we experience, and it acts on all objects of mass. So any object that has mass is attracted to any other object that has mass. We don't really feel the effects of gravity because we're so used to it. But gravity just is this force that acts to keep everything grounded, basically. So what comes up must come down. That's because of gravity. So it's force that pushes everything downwards and keeps everything where it is, basically. Keeps your pen on your table. That's because of gravity. So we have a gravitational field strength that comes from that. Gravitational field strength is specific to the Earth. So for the Earth, it's 9.8, but for all planets, it's different. So the gravitational field strength is the strength of our gravity. Okay, so it's the strength of the weight that acts, of the force that acts downwards on us all the time. Okay, so there's a force that acts downwards on us all the time, which is called gravity. And because it acts downwards on us all the time, it produces our weight. Yeah, so it produces our weight. That's where gravity really comes into effect. Can you go back and re-explain the question after the master piston one? So I think this is the one that you mean. I think this one. Yeah, so the pressure in the liquid applies a force to move each slave piston. How does the size of the force compare to the force applied by the master piston? So how does the force compare from the slave piston to the master piston? Slave piston to the master piston. Well, because we have a bigger area, so the force is larger. So if the force on the slave piston is larger, the area of the slave piston is greater than the master piston. So any other questions? What level would pressure equation questions be on the AQA exam? They would still be in foundation, I believe. So yeah, the calculations would be foundation, but the kind of qualitative, wordy answer about how pressure changes with depth would be higher. What year group is this topic? Year 11. Do I have to use 9.8 newtons per kilogram, or can I use 10? No, you cannot use 10. You must use 9.8, or more accurate, 9.81. They won't accept it if you use 10 because it's too much of a kind of round up, too much of an estimation. I think that's all of them. Yeah, okay, so I think that's all the questions. If you do have any more questions, do put them in the chat, but I'm going to move on. Okay, so here we have a question that combines a lot of different areas of physics. So I was saying that kind of pressure is one of those topics in physics that combines lots of different topics together. So you can see that we need to find a volume, then we need to find a mass, then we need to find a weight, and finally we need to find a pressure. So the question talks about a cylindrical drum of radius 40 centimeters. So that's our first kind of key bit of information, is that the radius is 40 centimeters. The height is 1.2 meters, and it's filled with petrol, which has a density of 737 kilograms per meters cubed. Now, first things first, whenever we see a really kind of massy question with loads of different values, we're going to check our units. Okay, this is always how I approach an exam question. Check the units. We don't want to fall at the end because we didn't read the question properly and didn't notice that some of the units were not what they were supposed to be. So top tip, always check the units. So as we can see, two of them are fine. We've got height in meters, which it should be, and density in kilograms per meters cubed, which it should be. However, our radius is wrong. Okay, radius should be measured in meters. It's distance. Distances are always measured in meters. So converting 40 centimeters into meters, we just need to do division by 100. So we get 0.4 meters. So that's the first bit, change the units. The second bit, or the first part of the question, is to find the volume of the drum. So find the volume of the drum. We've been given the equation for the volume of a cylinder, which is V equals pi r squared H. So to find our volume, we need to do V equals pi times r squared. So remember, our r is our 0.4. Times H. So H is our height of our drum, which is 1.2. So what would the volume be? Work it out on your calculators, put it in the chat. What would the volume of our cylinder or our drum be? So the answer would be 0.603 meters cubed. So remember, volume is always measured in meters cubed. Now we need to find the mass of the petrol in the drum. Using the equation, mass equals volume times density. Mass equals volume times density. Well, we've already worked out volume and we've been given density in the question. So we need to do our volume, which is 0.603, times our density, which is 737. So to find our mass, we times those two numbers together, work it out on your calculators. What would the answer be? It would be 444.5. Okay, so the mass is 444.5 measured in kilograms. And then we need to work out the weight. So the weight is mass times gravity, or gravitational field strength. So weight equals mass, which is 444.5, times gravity, which is 9.8. So what would the weight of our petrol be? So when we times those two numbers together, we get 4,357. Okay, so that's measured in newtons because weight is a force. Force is always measured in newtons. Now we have our weight, we can finally work out our pressure. Now you might see that this is a different equation to what we're used to. It's saying that pressure is W over A. However, all they've done is replaced our normal F, force, with weight, because the force that is acting is actually just weight. So pressure equals force divided by area. So pressure is 4,357, but what is the area? Well, the area is the area of the surface that the pressure acts on. So the surface that it acts on is the floor of the cylinder, which is just a circle, right? The floor of a cylinder is just a circle. So the area of a circle is pi r squared, where our r is 0.4, which is the radius of the drum. So the pressure all acts on the floor of our cylinder. Okay, the pressure is acting on the floor. So we need to find the area of the surface which the pressure acts on. So to find the area of a circle, we do pi r squared, where we know that our r is 0.4. So pi times 0.4 squared is what? So what would the answer to that entire equation be? So when we divide the top by the bottom, we get 8,668 pascals. So that's how to do a 4-part problem, which includes you having to go from one step to another using lots of different equations that you've learned throughout your time learning physics. So it is a very, very complicated question with lots of different parts and requires a lot of concentration. However, they have set it up quite nicely for you because they've rearranged the equations. So hopefully that makes sense, and that can be a typical GCSE question that could come up. So remember, in a GCSE, it's not always going to be one topic and then you have a question on it. They can combine topics. So I think we'll stop there because that's the end of the webinar. Hopefully you've learned a lot today, and thank you for listening.
Thank you, Preshayla. Thank you very much, everyone, for joining us. Remember, all of our sessions are recorded and uploaded onto our YouTube channel, so you can always rewatch later if you need to. All right, have a lovely afternoon, everyone. Thank you. Bye.
Thank you. Bye.